Alright, let's keep going with Chapter 8, Section 8.3, Logarithmic Functions as Inverses. So, what we're going to learn here, we're going to learn to write and evaluate logarithmic expressions, and we're going to graph them as well. And logarithmic, the shortcut for that, what we say is just logs. So anytime you hear the word logs, you're thinking logarithmic, and we'll learn what logarithms and logarithmic functions, as well as the common logarithm, what all of those things are in a little bit. But first things first, let's solve each equation and then graph some relations. So section 1, 8 equals x cubed. You guys know how to do this. Cube root it. Cube root it. 2 equals x. And then the second one here, y equals 5x. Let's go ahead and find the inverse first. So x equals 5y. So x over 5 equals y. Let's go ahead and graph both of these things. The first one, make a dot at 0. Go up 5 and over 1. That's 5x. And then the inverse is go up 1 and over 5. 3, 4, 5. Also through 0. So that's the graph of the relation and its inverse. Your job, 6, 7, and 8. Pause the video when you're ready to go. Press play again, and we'll get started with 8.3. Alright, so we're going to learn about logarithms first with an example here. Okay, so I think you've all heard of the Richter scale. It measures how much energy is in an earthquake. Alright, and so a magnitude of 5 releases about 30 times more energy than a magnitude 4. Okay, it's not just one more energy point than a magnitude 4. Okay, so it's a multiplier. So between 4 and 5 is 30. To go to 5 to 6, that's 30 more times. So between 4 and 6, it's not actually 60. It's 900 because it's times 30 and times 30 again. So we have the formula E times 30 to the whatever magnitude we have here. All right. So let's compare some earthquakes. In 95, we had an 8.0 earthquake in Mexico. And in 2001, we had a 6.8 earthquake in Washington State. Let's compare them. All right. So Mexico's was, remember that it's E times 30 to the whatever the magnitude is. So this was 8.0. And we're going to compare that, so we're going to divide it, E times 30 to the 6.8. All right, so if we have our ratio here, E's cancel. And remember what we do with the exponents if we're dividing, we're going to subtract them and get 30 to the 8 minus 6.8 is 1.2. All right, so it's going to be a little bit more than 30 times as much. Let's find out exactly. Oops, where's my calculator? There it is. 30 to the 1.2. All right, so the Mexico earthquake was about 59 times as big as the Washington State earthquake. All right, so that extra 0.2 almost doubled than if it was just as 30 to the first power. So it gets bigger really, really fast, right? And we've seen that with our exponential graphs, where things get bigger really, really fast. All right, so you're up. Same ratio. Do the same ratio to compare the Alabama and the California earthquakes. All right, so now that we've seen that, we're looking at what a logarithm is. And so just like in the earthquake examples, we're trying to find the exponent. That's what this is. So if we have y equals b to the x, where x is the exponent, if you rewrite it where x, the exponent, is by itself, we would rewrite it using a logarithm base b of y. That's how we say it. Log b of y equals x. All right? Now, a couple things here. B can't be 1. All right? And b has to be bigger than 0. All right? So just remember those rules. All right, so let's rewrite this. Logarithmic form for 25 equals 5 squared. So what we're going to do is we're going to get the exponent by itself. So 2 equals log base 5 of 25. So this says, how do I get from 5 to 25? I would square it. Right? That's how we're reading the logarithm equation. So log base 5 of 25 equals 2. That's logarithmic form. Your turn on understanding check 2, A, B, and C. Get it in logarithmic form. All right, so now we're going to go the other way, and we're going to evaluate the log 8 of 16. So we're going to say 8, what's our exponent to get to 16 on this one? All right, it's not going to be squared because 8 squared takes us too big. So what we're going to look for, are there any common exponents in 8 and 16? And it's actually, 8 can be written as 2 cubed. Still have the x there. And 16 can be written as 2 to the 4th. All right? So if we can get the base the same, what we're allowed to do is just cancel them out. And we have 3x equals 4. So x equals 4 divided by 3. So the key on these is get the base equal to each other on both sides. See if you can do it on understanding check 3. All right, so now we're going to use the common logarithm. So not most times, but a lot of the time, we're going to do logarithms using base 10. All right, and we use that so much, in fact, that if you don't see a base down here, if it's missing, we assume that it's the 10. All right, and if you look on your calculator, bring that back up, we have it right here. The log button, that's log base 10, and you can see the inverse of that is 10 to the x. All right, so the log is log base 10. All right, so let's use that for this problem with pH, a chemistry problem. Here's our equation, negative log of the hydrogen atoms. All right, so let's figure this out. Let's compare lemon juice, negative log of 2.3, to milk, negative log 6.6. So we're going to grab our calculators and we're going to put both of these in. So the first one is 2.3, so negative log 2.3. And we have negative log 6.6. All right, so this is the concentration of the hydrogen atoms and the concentration of our hydrogen atoms again in milk versus the lemon juice. All right, so on these, which one is more acidic? Lemon juice is, because it's less negative actually. Okay, so even though it's the smaller number, 36 versus 81, it's closer to 0. So less negative, has more acid in it. And that makes sense, right? Lemon juice is acidic, less so than milk. All right, so just putting it into your calculator for this problem. You're going to do the same thing here for seaweed. All right, logarithm of 8.5. All right, so now let's graph them. Second objective we've got here. So this pink graph here is the exponential graph of y equals 10 to the x. From last section, we've learned how to graph these. 10 to the 0 is 1. 10 to the first power is 10. This one back here would be 1/10. 10 to the negative 1 is 1/10. All right, and remember we have a horizontal asymptote of y equals 0. So now when we do a logarithm, we're doing the inverse. We're rotated 90 degrees here. So now instead of a horizontal asymptote, we're going to have a vertical asymptote of x equals 0. X equals 0 going up. Look at the point, 0, 1, just switches to 1, 0. 1, 10 switches to 10, comma, 1. All right, so same thought process, just switching the x and the y's. And in fact, when you graph these, I think a lot of times it's easier to rewrite this as 2 to the y equals x. And then go ahead and make yourself the same t-table you did for your exponential graphs, but start by doing 0, 1, and 2 here for the y's, as before we did it with the x. So 2 to the 0 is 1, 2 to the first is 2, and 2 squared is 4. Let's go ahead and graph it. So we've got 1, comma 0, we've got 2, comma 1, and we've got 4, comma 2. And remember, we know that we have a vertical asymptote at x equals 0. Definition of a logarithmic graph, it's always going to be like that. And so we're going to hug that asymptote and then take off and flatten out. Instead of taking off vertically, now we're going to flatten out as we go up. And we're actually going to go vertical down here on the asymptote. All right, so see if you can do the same thing. Graph y equals the log base 3 of x. All right, so a couple characteristics here. This is what it's saying here. Asymptote is x equals 0. But what about if we have some transformations here? So remember, the x minus h part is the part that's moving us sideways. And so if we can find h is going to be our new asymptote. All right, so whatever h is, the opposite of the sign. So if it's -3, the asymptote's at 3. If it's +2, the asymptote would be at -2. The domain is always going to be greater than the asymptote, unless there's a negative in front of the x, which we don't deal with a whole lot. Okay, so we're greater than the asymptote, and the range is all real numbers, because we're going to go up and down forever. So let's see if we can graph this one here. So first things first, I'm going to find the asymptote. Okay, the asymptote is going to be x equals, right here, +2. So I'm going to go ahead and throw my graph up there. And there's my asymptote at x equals 2. All right. Next thing I want to do here is the same sort of t-table. Okay. And I want to use my, and I think it actually is helpful to rearrange this. So 6 to the, you know what? Let's do it without rearranging it. Let's learn how to do it without doing that. So here we go, x and y. All right, so first things first, let's make x 3. All right, one more than the 2, and I think you'll see why in a second. Because log base 6 of, if I plug in 3 minus 2 is 1. Log base 6 of 1, 6 to the 0 power gives me 1. So this turns into 0, because 6 to the 0 is 1. And then we still have that plus 3 hanging off on the end, so 0 plus 3 is 3. All right, so if x is 3, y is 1, 2, 3. There's our first point. All right? And that makes sense as well, because in our parent function, we should have 1, 0. We went right 2, so that got added by 2. And we went up 3. Okay, so that turned into 3, 3. All right, the next thing you're going to do is, what number would you plug in for x so that if you subtracted 2, you got 6? Because we want this to be 6 to the 6. So log base 6 of, if you pick 8, 8 minus 2, log base 6 of 6 is just 1, and then we can add 3. 1 plus 3 is 4. So 8, 4. 4, 5, 6, 7, 8, 4. And that's actually enough, because we have our asymptote and 2 more points, so that's 3 points. We always need 3 points here with these, but the asymptote can count as 1, and we can graph it, and there we go. So a little trickier. See if you can put it all together here for y equals log base 3 of x plus 3. All right, that's it. That's all there is for 8.3. Any questions, we'll go over it in class. Good luck.